All right, everyone. Welcome to this class in Mathematics 1, our last lesson of integration today. So we'll start with a brief warm-up. Let me just unfreeze that. You can actually see what I'm talking about. Now you should. Good. So here's a warm-up exercise. See if you can find the value of this integral. And as usual, there's also a tweetback quiz asking you for your answer once you have that. There's 10 answers already, so for those who are done, here's the second warm-up question. And of course, there's also a second quiz for that one. Just in case you need it, for the second warm-up question, I've added a small hint about a value of the cosine that you might not remember. Just a quick check, show of hands, who's done with the first warm-up problem? Who's still working on that first problem? All right, who's done with the second one? And who's still working on the second one? Good, we need some more time. So once again, a quick check. Who's done with the second warm-up problem? Who still needs some more time for that? All right, so let's add 3 minutes, and then we'll see what results you have. All right, I guess we can start the countdown. So 1 more minute to submit your vote, and then we'll take a look at those questions. All right, so here's the results for this first warm-up question, this one here. Most of you are saying LN2, some are saying the negative of LN2, and that's pretty much almost all the answers that you gave. Let's have a quick look at that one. So you have basically you have 2 methods that you can use if you, or maybe let's say 3 methods you can use to evaluate an integral. First, it could be something more or less elementary. Yeah? You could just look at that and see, well, this is integrating a polynomial or this function. I know how to integrate that, so I can do that in a straightforward manner. I know an antiderivative more or less right away. Maybe you have to figure out some constants, but that's it. That doesn't seem to be the case here. So then it's either integration by parts or it's some suitable substitution. in this case, integration by parts, if you do that, well, it's basically something like sine times 1 over cosine. And 1 over cosine, well, whether you try to integrate that or whether you try to differentiate that, it will probably get more complex. So I wouldn't go that way, at least not as a first attempt. So my first guess would be something like, let's see if we can find a substitution that works. And of course, again, there's pretty much two things you can do. You can either try to substitute, let's say, t equals the sine of x, or t equals the cosine of x. One of those might be the right attempt here. And if you look at the hint, this is pretty much giving it away. Right? If you do the substitution t equals cosine of x, and you also want to use that substitution for the limits, well, there's your cosine of pi over third. Right? That might be where you want to use that value. So looking at the hint, that's the first thing I would try. Generally, if you try one of these attempts, yeah, it's hard to predict which will work and which won't work. Even with a lot of experience, it's still hard to say what works and what doesn't. So if you try that, and after the first step you find you're getting nowhere, and maybe even after the second step you find it's even getting more and more complicated, and you're not sure whether this is going anywhere, maybe it's a good idea to just start over with a new attempt, right? Before you try to make that one attempt work over and over and over again, losing a lot of time if it's not the right way. Just start over, try again, use something different. See if the first step seems promising, and if it does, try more of that. If it doesn't, maybe try something else first. All right, so what we do here is we want to use a substitution. And our substitution is going to be, let's call it t, is going to be the cosine of x. Then you know we've introduced this formalism here, where we differentiate this expression that we use for the substitution with respect to the original variable. So we're at dt over dx, meaning we differentiate this cosine. Well, differentiating this cosine gives us the negative sign, right? So now again, the step that comes now is just think of that as a formalism that helps you remember the rule. Of course, you can also remember the formula that is in the lecture notes, but personally I find that more complicated than just going through that formalism. Because the question came up on tweetback, this solving for dx, at least in this class, this is just a formalism that doesn't mean anything really. There is a theory that you can use to explain what is really happening here. Pretty deep and beautiful theory, but we're not going to cover that in this class. If you want to do that, I'd advise you study mathematics. I think we got to do that in the third semester, so you will need to have quite a few basics to get to that point. That's why we don't do it here. Okay, so let's go on with that. Again, think of that as a formalism. We just solve that formally for dx without thinking what this dx actually is. So we're just solving for that. We get this is dt over the negative sine of x. Right, and now if you look at that expression here, you can see if we replace dx by this, yeah, we get 1 over sine, and we have a sign here, so those will cancel out. That seems promising. Okay, so let's try to do that. Maybe let me just copy that quickly. All right, so what do we get? I already mentioned, I don't think we have seen an example where we have limits. I already mentioned you can also use the substitution on the limits. So in that case, t is the cosine of x. Those limits are in terms of x. So if we do the substitution, we'd rather have them in terms of t, right? That means what we do here is we replace those limits by substituting them into the t expression, right? So that's cosine of 0 That's going to be cosine of pi over 3. And then we have sine of x here. We replaced the cosine of x by t. That's our substitution. And then we have this dx expression here, and we replace that by dt over the negative sine. And now that sine here, that cancels out. So we are left with an integral expression in just one variable. And that is 1 over t, well, minus 1 over t, dt. To make things even more easy, let's take out the minus. And for the boundaries of the integral, the cosine of 0, is 1. And the cosine of pi over 3, here's your hint, that is 1 over 2. Right, and you do know how to integrate 1 over t, that's just the ln. So what we get is minus the ln of t from 1 to 1 over 2. And you can see the upper bound here is actually lower than the lower bound. Right? So we're kind of integrating backwards, but that doesn't really matter, just a formalism. Okay? So at this point, all there's left is evaluate the result. So what we have to do is substitute the upper bound, so that's going to be ln of 1 over 2 minus the lower bound, ln of 1. Now, ln of 1 is 0. What about that ln of 1 over 2? You notice that doesn't show up anywhere here. So what we're left with at this point is minus, oops, wrong color, is minus ln of 1 over 2. And by the way, this would have been a totally acceptable answer. You could just stop there. Right? I just wanted to show this reformulation in case you want to use that somewhere else. The idea is to write 1 over 2 in the form 2 to the minus 1, and then use laws for doing ln calculations, where you can take out the exponent. So this is minus 1 ln 2. Right? So this minus 1 here, this minus 1 is what I'm taking out here. So what we get in the end is ln 2. So apart from the sign, most of you get that right, I'd say. All right, any questions about this one? Yes? Yeah. So yeah, as an alternative, so what I'm doing here is I'm updating the bounds to be in line with my substitution. I don't have to do that. I could also just forget about the bounds during the substitution thing, then compute the solution, and at the end, so when I'm here at this step, undo the substitution, right? So then instead of t, I'd write cosine of x into the expression I have integrated, and then I'll just solve with the old bounds. I could also do that. Any other questions about this one? Just out of curiosity, did anyone try a different approach? Another substitution or integration by parts? Did it work? Yeah, which one did you try? Mm-hmm. So basically what you did is actually a substitution, you just made it quicker. You didn't write it down. I'd say that is, yeah. Sorry? Okay. Another interesting approach. Good. So usually for integrals, and of course for lots of other problems, there is more than one approach that will work. Of course, I usually have one specific approach in mind that I hope you will find and that I hope is easy enough. But often other approaches also get you a right result. Often it's a little more work to do that, but not necessarily, of course. And of course, any approach that works and that is sufficiently well explained and justified will give you full marks on that. Good, let's take a look at the second warm-up then. So here's your answers about that one. Almost 70% found the right answer here. So again, if you look at that expression, I'd say the complicated part is basically this one here, right? Sine of ln, that doesn't look very nice. I have no idea how to integrate that. So I'd have to simplify that a little. And one possible simplification would be to replace this ln with a substitution, right? And if you're at it anyway, you can as well integrate this, this constant here into your substitution so that you don't have to worry about that when doing the integration step. And that's what I did here. So my substitution was, let's substitute t for pi over 2 ln of x. And then again, if I do the formalism, dt by dx, what I get is pi over 2 times 1 over x. And so that means dx is equal to, let's see, 2x over pi dt. So if I replace dx by this expression, and you see I'm getting an x here in the numerator, and I already have one in the denominator, so those will cancel out. So I'd say that looks promising. Right? I'd go on with that. So let's copy that integral. Just a second. All right, so now if I do the substitution, what I get here is, of course, the sine of t, right, instead of this ln expression over x, and then instead of my dx, I replace that with this expression I computed, so 2x over pi dt. And again, you can now see that x will cancel out, so basically I'm left with the integral over a sine expression. All right. As for the bounds, let's see. What we have here is, let's just write those down once, pi over 2 ln of 1, and then pi over 2 square root, ln of square root of e. Okay, going on with that. So let's take out all the constants before the integral. This is 2 over pi. The x cancels out. I'm left with an integral over sine of t dt. And for those bounds, obviously the ln of 1, this one here, this is 0. So that's easy. For this expression here, ln of square root of e. I would know the ln of e, of course. That's easy. That's 1. But what about that square root? Well, how do I get rid of that? Basically, same trick I've used before. So what I'm doing here is I write that as, let's just keep the pi over 2. I rewrite that as ln of e to the power of 1/2. And then I can again use those logarithm rules to take out that 1 over 2, and I'm left with ln of e. I know what that is. Right, so that's the idea here. Let's copy that once again. So this is pi over 2 times 1/2 times ln of e, and ln of e is just 1. Sine t dt. Okay, that's fine. You do the integration, 2/pi. Now the integral of the sine is the negative cosine from 0 to, and this evaluates to pi/4 times 1. Right, so this is where this cosine of pi/4 comes in. Okay, so let's see, this is 2/pi, and then we get minus the cosine of pi/4 plus the cosine of 0. So 2/pi. I told you the cosine of pi/4, that's the square root of 2/2, minus the square root of 2/2. And the cosine of 0, that's 1. Right, so if you reformulate that slightly, you'll get just the expression that you have here, 2 minus the square root of 2/pi. All right, any questions about this one? Did anyone try a different approach here? Successfully? No, okay. Good, so let's have a quick look if there are any questions on the tweetback. Okay, quick question about this replacement here. So someone is asking why do I replace those by those bounds here? The answer is this new integral. So this old integral is in terms of x. That means the bounds are also in terms of x, right? I could add something like x from 0 to pi/3. The new integral after substitution is going to be in terms of t, right? We have this dt here instead of the dx, so that means we're integrating with respect to t. And that means the bounds will also have to be with respect to t. So we are using this substitution formula, right, to compute the corresponding t bounds for the x bounds that we have. So these bounds, I need a different color. These bounds here are now with respect to t. Right? And that's why I'm doing, basically I'm doing the substitution, I'm applying the substitution in the bounds too. I could also not do that, and then undo the substitution. So at this point here, I could undo the substitution by replacing this t with cosine of x, and then evaluate the integral using the old x bounds. Basically the same thing happens here, of course, right? Just delaying this evaluation. Doesn't matter which approach you choose. Technically, if you do that last thing, right, going here and then undoing the substitution and then using the old bounds, of course you don't have to compute the new bounds. What you would then do technically is please don't add any bounds here, because that would be wrong, right? So if you just keep writing the x bounds after the substitution, that's not correct anymore. What I would do in that case, just as a matter of notation, I would first compute the integral without any bounds. So I compute the indefinite integral. And then I'd use my result to compute this integral. Okay? Same thing, just the notation is a little different to make it look right. Okay, any other questions that I can answer? Why the signs? Where are the signs? All right, so the question is, what about those signs? I'm guessing you're referring to those here, minus cosine of pi/4 plus cosine of 0. Well, we have minus cosine of t as our antiderivative. And then we need to first substitute the upper bound in there. That's where the minus of cosine pi over 4 comes from. And then we subtract the lower bound from that. So that's basically that plus here is a minus minus, right? This comes from minus the lower bound, and then the lower bound is minus cosine of 0. So the double minus turns into a plus. That's where the signs come from. I hope that answers the question. All right, that doesn't seem related to this problem. So if there's no more questions from the audience, let's take a look at some other examples. I took a look at some of the old exams, and there's quite a few integration questions on those. So maybe let's start with a pretty recent one, 2021. This is problem 10. The problem statement says, determine the following indefinite integral. I won't write that down. Document your solution approach and explicitly state the integration techniques you are using. So even if I wouldn't have written that sentence there, you should still say, I'm using integration by parts. I'm using substitution. This is my substitution, right? These are my functions for integration by parts. This is what I'm trying to do. Let's hope I can do it correctly. All right, so here's the integral. Integral over 2x sine of x squared cosine of x squared times sine of x squared times sine of x squared plus 2 dx. Try to solve that. Looks a little intimidating. So again, I have opened the tweetback. This time I'm just asking for how hard you found that, basically as an indication of when you're done. All right, quick show of hands. Who's done with the problem? Who would like some more time? Okay, maybe just give it 2 more minutes. One more minute. All right, so let's take a quick look at the results here. Most of you found that hard. Interestingly, there's always someone who finds it easy. So I'll admit, when I first looked at that, a couple of years after I actually did this exam, I also thought, it seems pretty hard. But if you look more closely, it's actually not. Turns out to be really easy, just looks terrifying. So what do we have here? Well, lots of sine x squares, cosine x squared, 2x. At first sight, I wouldn't see how to do integration by parts with that, right? Whatever I choose for the parts, integrating that seems quite a challenge. So maybe not the first idea I'd try. So then probably substitution. What could I use for substitution? Well, I could use something like the sine of x squared or the cosine of x squared maybe, or maybe just x squared. Now, if you want to go for substitution, basically that works if the derivative of the term that you substitute is already contained in the integral, more or less, right? Because that's going to hopefully cancel out later on. So if we take a look at that, we find there's a lot of sine x squareds in there, but only one cosine x squared. So if I would take this term here, say, well, let's do substitution and use t equals sine of x squared, then if I differentiate that, what would I get? You can quickly do this roughly in your head. The derivative of the sine is the cosine, right? So I get something like cosine x squared. And then using chain rule, I multiply with the derivative of this argument, x squared. So that would yield 2x. And now looking at the integral, well, here's my cosine x squared. That looks good. And here's my 2x. So that would probably work. Let's give it a try. And all those signs here, those will basically go away through the substitution. Okay, so let's just try that. So here's what I'm doing with the substitution. What do I get? well, let's copy those things I cannot replace by my substitution, 2x cosine x squared. Then I have sine of x squared, this one here. I replace that by t, times. Here I have sine x squared, so t times t, plus 2. Can't do anything with that. And then for the dx, still need to solve that. So dx in that case is dt over 2x cosine x squared. Right, so I replace that by dt over 2x cosine x squared. And what happens is, well, this term cancels out. And what am I left with? Well, what I'm left with is t times t squared plus 2 dt. Or even more easily, t to the third plus 2t dt. Well, that is easy to integrate. I hope you agree with that. So what we get here is t to the power 4 over 4 plus 2t squared over 2. So the 2 cancels out, left with t squared plus some constant. And then I just undo the substitution. So remember, t was sine x squared. So what I have is a quarter sine x squared to the power of 4 plus sine x squared to the power of 2 plus some constant. Right, so basically what this really is just a simple polynomial in disguise. That's why I say it looks terrifying, but it's actually really easy. All right, any questions on that one? That does not seem to be the case. No questions on TweetPeg either. One question that has come up is someone is asking me to do E14.7. If you might remember, if you have already looked at the sheet, this is E14.7. Of course, if you have any questions about that, we can also discuss that in exercise class later. But as the question has been asked, there is the option of either doing that right now or doing one more example from the exams for integration. So I just set up a quick vote for that. Should we discuss E14.7 in class right now or not? If you'd like to vote on that, please just take out your tweet back and let me know what you think, and then we do whatever you think. I'll give you 30 seconds from now on. And then I'll do whatever you want me to do. All right, here's the results. Most of you say no. As I said, you're free to ask questions about that in exercise class later. So let's go on with one more exam example then. I think this would be a good choice. So this is 2019-1, problem 10. Right, and the question is, evaluate the following integral. The integral is 9x squared ln 2x dx, and the bounds are 1 over 2 to e over 2. And again, the problem statement specifically asks you to give a brief description of the integration method and describe the basic steps. So basically, What I wanted to see here is your calculation, or at least the basic idea of that. quick show of hands, who's done with that problem? Who would like some more time? Okay, there's quite a few. Let's give it a couple more minutes. So let's say take one more minute. So here's your feedback on that. Pretty mixed, obviously. I'd say leaning a little more to the easy side, but just very slightly. So let's see, how do we solve that? If you look at that integral, again, doesn't seem to be an elementary integral that I would solve right away. So it's either substitution or integration by parts, probably. Integration by parts, we need two functions, one that is easy to integrate, one that is easy to differentiate. And hopefully we'll make the whole thing easier. This here is a polynomial. That's surely easy to integrate and differentiate. And here we have an ln function, and functions of that kind are usually easy to differentiate and somewhat harder to integrate. So my first try for integration by parts would be integrate that, differentiate that. Let's see if that makes it any easier. Thinking about substitution, I wouldn't see any immediate idea substituting that doesn't make a lot of sense here. If I would substitute, then it's going to be this ln term. That might be worth a try, but I don't think the x's will cancel out properly if I do that. Right? So I guess integration by parts is the more promising approach here. So let's try that. So let's say this is f prime. This is g, and remember the formula for that, integration by parts, that was the integral of f prime g is the same thing as f times g minus the integral of f g prime. Very short form. So let's do that. That means we first have to integrate f prime, 9x squared. We'll do that. Well, x squared integrated is x to the third over 3 times 9. We can cancel out a 3, so that's 3x to the third. And we just keep the g times ln 2x. Right, so that's the first part. And then we subtract a new integral, same bounds, where again we integrate f prime. We did that already. That was 3x to the third. And then we multiply by g prime. So we need to differentiate that. Well, the derivative of the ln is 1 over the argument, right? So it's 1 over 2x. And then we apply chain rule. We need to multiply by the derivative of 2x, and that's just 2. And as you can see, what happens here is when we get something over x, this nicely cancels out with part of this term, so we're left with a polynomial. And that should be easy. Right, so we get 3x to the power of 3, and by the way, I should also add the bounds here. 3x to the third times ln 2x, let me evaluate that later, minus, I'll just write it down once again. So we have is the 2 cancels out, the 3 we'll keep that, we just put in front of the integral here. And the x cancels out with x to the third, so we're left with x to the power of 2 dx. Okay, so what we get is, I'll write it down once again, this term 1/2 e over 2 minus 3, and then integrating this yields x to the third over 3. So I can just forget about that, right? Okay. And now I'm ready to substitute my bounds and get the final value. So substituting e over 2 here in the first expression, that yields 3e to the power of 3 over 2 to the power of 3 is 8 times ln 2 times e over 2 is just e, minus, and then the lower bound, that is 3 times 1 over 8, 1/2 to the power of 3, times ln 2 times 1/2 is 1, so it's going to vanish anyway, minus, and then x to the power of 3, so this is e to the 3 over 8, minus 1 over 8. And I just have to simplify that a little bit. Let's see. So ln e is 1. That means we have 3 over 8 e to the power of 3 here. Right, this is 0, so that term just vanishes. And then we have minus 1 over 8 e to the power of 3 and plus 1 over 8. So consolidating those two here, we get 2 over 8 e to the power of 3. 2 over 8 is 1/4. So this is 1/4 e to the third plus 1 over 8. Just out of curiosity, who of you got that right? Great. Okay, any questions about that? Good. So just 5 minutes left. Probably doesn't make sense to start something new. Maybe just a couple words about next week. So as I said, this has been the last new topic that we have discussed. No new topics next week. Instead, we'll do Q&As and exam questions and whatever else you want to do. For the questions you might have, I have already opened another tweetback chat wall for next week. It would be great if you could just post all your questions in that chat wall if possible. If you have already asked in the past and I haven't answered yet, probably because it just didn't fit to the topics, please just post that again to the new thread so that I have it all in one place and I don't have to wait through all those large chat walls of the past weeks. If you want to see any questions on the exam that we haven't discussed yet, on the past exams, there is a thread on the Moodle forum where we collect all those requests. So just please add your request to the list, and I'll add that question to my list, and hopefully we'll have enough time to tackle that next week as well. All right? It would be a great help if you could do that, possibly before Monday, so that I can come up with a plan of what to do on Monday, and then we'll see how that goes. Go on Tuesday and Thursday, of course. All right, any more questions? Yes. Will there be an exercise class next Thursday? The answer is yes. Yeah, there's a regular exercise class next Thursday, and of course you're welcome to bring all your questions for all over that semester to that exercise class that I haven't been able to answer otherwise. All right, so I'll see you in exercise class.